Welcome back, guys. So, what if your mom or dad decide, you know what, we're going to go get some dinner, going to go hit a drive-through for dinner. So they're out getting in the car, and they're on the road in the car, driving along, right? Thinking about what to get. There's a roadway, and they're just kind of moving along. And so they get to wherever they're going. I don't know what your favorite fast food place is. So they get there, and maybe there's some sort of golden thing on a sign out front. Who knows? Whatever you like. And so they get there, and they got the little drive-through window, and what are they doing there? They're waiting. They're slowed down. They have to spend some extra time here. So if you consider, well, how long would it take them to drive there and back if they didn't stop? And compare that to how long it would take them to drive there and back while they have to stop at the drive-through. They have been slowed down. There is a resistance to that flow of your mom or dad in the car. So this actually kind of does work like an analogy for an electric circuit, where you have a current flowing and you have something slowing down the current, the stop at the drive-through window. Well, you know what's going to happen, right? On the way home, after picking up the food and it's all yummy, and your mom or dad realize, you know what, the gas light is on the dash, so they need to stop and get gas. So they stop at some gas station, and they got the little pump thing, and so they're here, and they're now filling up the gas tank, doing their thing, right? This is up in the background. So they have stopped again. So on their path to get back home, they have been slowed down here at the drive-through, and they have been slowed down here at the gas station. And what's going on is they have multiple places where they slow down, and it's one after the other. And what happens is it slows the flow even more. So this is just like when it's one after the other. This is by definition what series connections are. A series is one thing after the other. And if you had yet another place, let's say there was an accident on the road, and so your parents are kind of headed home, food's in the car with them, and they're here sitting in traffic, eating all your French fries, waiting with other cars. They've been slowed down even more, and because there's some sort of accident here, and so slowed down even more, and it's yet one after the other, even worse. And so by the time they get back home, they've eaten all your French fries, and your burger's cold, and it's just no fun. But you see what's happening. We have multiple things, one after the other, slowing the flow, right? And if we were to add yet one more thing that's acting like a resistor, the current would be reduced even further. Okay, so this is what we're talking about, series circuits. All right. Let's get serious about the series circuits here. Let's start with a diagram. We're going to need a circuit. You know what that is. That is your voltage source, right? So what we're going to do, I'm going to have a resistor here. Come out here, and resistor here, and let's just do one here too. Okay, and we have a complete circuit. Now, I'm going to label this voltage of the source. This is like a battery or a power supply. I'm going to label this guy R1 and R2 just to give them names so we can talk about them, write about them, work with them. R3. And right away you have to notice there's only one pathway for the current. So current's going to flow out of the positive terminal of the battery. There's a positive and there's a negative. And so current flows that way. And there's only one path. There's no choices or forks in the road. Okay, that's an important point about a series circuit. If there were a decision, a fork in the road, multiple paths to take, then where the thing splits would be called a junction. Never mind that. That doesn't apply here to series circuits. But what that means is that all locations in the circuit have the same current flowing through them. So there's no choice. This current coming out of the battery, all of it goes through R1, and all of it goes through R2, and all of it goes through R3. Same current at all points in a series circuit. That's also important. Okay. Write that down. And we can label that as well. So there's going to be that current and this current, and those are all equal. This is I1, I2, and I3. And because of this same current at all points, then what we know is I1 equals I2 equals I3, which equals I. Just the current flowing out of the battery. Maybe you want to label the I of the source. Sometimes this is called the terminal current coming out of the terminals of the battery. I'll put an S here so it shows up. Okay. So current's pretty easy to deal with because you can just see it and just logically come to this conclusion. Now, what you need to do is some more about this, recall that the voltage source is where energy is added to the charges. Remember, resistor number 1 is not using up some of the current. That's a wrong way of saying it. It doesn't use up current. Current is not used up. Oh, my 2 looks like a blob now. Wow. 2. Sorry about that. Now, current is not used up. The current is the same everywhere. The same amount of current that's leaving the battery is the same amount that returns to the battery. Those charges are not used. The energy that they carry is used. And so we have to talk about that. So the voltage source adds energy. We have energy in over here on this side. And then these resistors all represent an amount of energy out over here. Each resistor takes some of that energy away. So while the voltage source provides a voltage gain, each resistor provides a voltage drop. Now, what we can say about all circuits is that the voltage gain equals the voltage drop. And we're talking about total amount here. Total amount of voltage gain and total amount of voltage drop will be equal. But we have a voltage source, which is our gain, and we have multiple drops here, so really the total drop is the sum of all the voltage drops, which equals voltage of R1 plus voltage of R2 plus voltage of R3. Now there's another way of looking at this equation. Voltage source equals the sum of those guys. And if I were to bring all the voltages to the same side of the equal sign, we're going to kind of ignore this in the middle now. Bring all these voltages to the same side as this guy. I have to subtract them from both sides. Minus V1, minus V2, minus V3. And what I should get is 0 on this side. So the sum of all voltages is 0. Well, that kind of makes sense. If I've given some energy here, then I have to lose that amount of energy by the time it gets back here. And that's what's going to happen. I'm flipping back and forth between voltage and energy, and you don't want to get them, you don't want to be thinking that voltage is energy. No, but it is related. Okay, so I can add some values of voltage to the circuit. Let me find a good color. I'll just use, okay, since voltage and energy are related, I will use red. Here's V1. And if we were to measure it with the voltmeter, we'd see that here, right? There is a V2. And we can measure it across resistor 2. And a V3. Measure it across R3. And so, here's our other voltage right here, right? Voltage of the source. If I were to measure that, I'd have to hook up my voltmeter like that across the power supply or the battery. Cool. So look what we figured out. We figured out the current everywhere, in our series circuit. This is an S. Come on, marker. This is the marker that never wants to work. I'm going to retire this guy. This is 3. That's clearly a 2. That's pretty good. And that's a 1. Okay. What else have we figured out? We figured out current. We figured out voltage everywhere. You know, either way you like to write this. If you like to write it this way, or if you like to write it this way, either one is accurate. Either one is correct. It's fine. Now, we're going to use some of this knowledge and start combining things, right? So, recall Ohm's law. And, you know, different ways to write it. The most common, V equals I times R, voltage equals current times resistance. So, from that, we can say that, well, the voltage drop across resistor 1 is equal to the current through resistor 1 multiplied by the resistance of resistor 1. And we can say the same thing about the other resistors also. 2R2 and 3 equals I3 times R3. Okay. So we have basically said, for example here, that V1 equals I1 times R1, and V2 equals I2 times R2, and V3 equals I3 times R3. Well, also we could say voltage of the source equals the current from the source multiplied by a resistance. Now, what resistance would we have to use? We would have to use a resistance that's equal to all three of these combined. So that's what we're actually going to figure out, is what is that combined resistance. So we're going to combine these, and we're actually going to see, okay, so voltage of the source, sorry, don't need a big S, need a big V, equals the current from the source multiplied by, check this out. Remember that the current is the same everywhere. So instead of writing for each of these guys up here, instead of writing I1, I could write IS, right? And what I can do then, even further, is I already know this right here, that the voltage of the source equals the sum of the voltage drops of the three resistors. So I'm going to do a little combining of things here. Sliding down on me. So the voltage source equals that voltage 1. Well, voltage 1 is IS times R1. And I have to add V2. Well, V2 is IS times R2. And I have to add V3, and V3 is IS times R3. Okay. So there's an important thing about to happen here. Watch this. I can factor out the IS, and I can say that, well, then it's IS times R1 plus R2 plus R3. And now, what I'm looking for is a way to describe the equivalent resistance. Remember, I was looking at this. I have a voltage of the source, a current of the source. What is the resistance of the whole circuit? How are we combining R1 and R2 and R3? You might already see the writing on the wall here. Remember that from Ohm's law, I can rewrite this guy as resistance equals what? Equals voltage divided by current. And from this, if I simply am talking about the voltage of the source and the current of the source, then the resistance is going to be the resistance of the whole circuit. And we call that equivalent resistance. So that's pretty darn cool. And I get that equivalent resistance from voltage source divided by voltage current, or current to the source, forgive me. And all I have to do to get this is divide both sides here by IS. And so here, cancel, cancel, and I get On this side, look, this is voltage source divided by current to the source, this, but that is equal to my equivalent resistance. Equivalent resistance is basically the resistance of the entire circuit, all of these combined. And look what I have on the other side. So the equivalent resistance of series resistors, you simply add them together. That's it. That's how you find the total resistance or equivalent resistance in a series circuit. Definitely, it got to be series. You have to make note of that. Okay. So, that's a pretty cool deal right there. Notice that adding resistors in series will increase the overall resistance of the circuit. And therefore, if you increase the overall resistance, remember how we sort of prefer to write Ohm's law? Current is the one that depends on voltage and on resistance. And so if you add another, oh, by the way, I probably should do ... because you can have any number of resistors in series, right? Well, okay, so if I add another one in series, then I increase the value of the equivalent resistance. The circuit has more total resistance, so that increases the value of the denominator. Therefore, the current will decrease. That's super important. I'm going to say it one more time. Make sure you write this down. Adding a resistor in series increases the total resistance and therefore decreases the total current in that circuit. Okay. That's huge. Make sure you understand that. All right, that's it for series circuits for now. Thanks for watching. I'll catch you next time.